Hello, I'm Dr. Mark Taylor and I'm a lecturer in civil engineering. So this is Unit 5 and we're going to look at alignment design. So Unit 5, alignment design, is going to look at geometry, alignment and route clearance. So the aims of this session, I'm going to describe the basic principles of alignment design. I'm going to provide examples of the stages of a railway design project. I'm going to detail the physics of railway curve design and discuss the relationship between curves, rail vehicles and applied Cant. I'll then describe transitions, clearances and buffer locking as a result of the curves in Cant. I'll introduce and give some examples of vertical alignment design too. So at the end of this unit, you should be able to summarise the stages in the design of a typical new build railway, explain the terms equilibrium Cant, Cant excess and Cant deficiency, calculate equilibrium Cant for a curve of a given radius and design speed, recognise the consequences of rail vehicles, travelling curves and inappropriate speeds, assess traffic loading, calculate the length of a transition curve, analyse whether buffer locking is going to be an issue, and propose vertical alignments over a typical section of terrain. So let's start off by looking at some of the basics of alignment design. So let's start off by reminding ourselves of some of the key definitions. So permanent way. This is the rails, the rail fastenings, the rail supports, the sleepers, the ballast, the drainage, and formation which together make up the guidance and support system for rail vehicles. In comparison, a temporary way is a track form laid during construction, as and when required to allow construction trains to be run, lifted and used, and not part of the final completed railway. This may also refer to railways associated with mining works, tunnelling works, or quarrying activities. The Border Railway is the longest new domestic railway to be built in the UK for over 100 years. The line was controversially closed in 1969 as part of the Beeching Cuts. However, the Waverley Railway Scotland Act in 2006 received royal assent in June 2006. The project was renamed the Border Railway in August 2008, and building works began in November 2012, with passenger service on the line beginning on the 6th of September 2015. The 30 miles of track sees passenger trains running from Edinburgh through Midlothian and into the Scottish borders for the first time in almost half a century. It takes passengers between Tweedbank and Edinburgh in less than an hour, and trains run half-hourly throughout peak times. So what I'd first like to do is show you some integrated engineering layout plans and aerial plans of the Borders Railway. Now, as you can imagine, this is a huge project, and you can see from this drawing that it's sheet 2 of 77 drawings. During the design of the project, there were many consultations with the public, and there were documents released to the public which allowed us to look at these proposals for the route. I'm going to show you some of these drawings just to help you understand what an alignment looks like and what an AutoCAD drawing that would eventually be produced in the office would look like. These are for preliminary drawings for consultation purposes rather than production information that would be used for actual railway construction. Here you can see an aerial layout showing the design superimposed over an aerial photograph of the land as it is at present. On this drawing we can see the radius of the curve, and note the blue and green boxes which provide details of overbridges and underbridges in this case. Here you can see a reverse curve and another 2 underbridges which look like they're for farming access for cattle. On this sheet, again an underbridge, an overbridge, but also an embankment and a cutting, shown in black. This section again has overbridges and underbridges, but there's also a tunnel that needs to be replaced. You can see from this image that the railway, or the new railway alignment, passes very close to this farm building. You can also see that it cuts across the farmer's land. So it's inevitable that the farmer is going to want some compensation for this. As a graduate civil engineer, the majority of your work will be maintaining the existing infrastructure that we have, a lot of it Victorian. The Borders Rail project, as I explained previously, was one of the first new railway projects in a long time. So, new railway construction, when it happens, what are the processes? What are the stages of construction? So in general terms, the stages of construction will start off with scheme appraisals. They'll look at the need for the scheme in the first place. Then we'll look at the feasibility of options in feasibility studies. Then we'll consider some outline designs. This will then be followed up with very detailed topographical surveys of the site, followed by detailed design work, and then eventually construction. So when considering HS2, the scheme appraisal looked at transport demands, in particular passengers and freight. They asked the question, is rail the best option? They then have been trying to outline the cost-benefit analysis, but they've also got to look at other factors like social, environmental, regeneration, etc. Feasibility studies are based on the best available information without detailed topographical surveys being commissioned. They look at potential route alignment options, then also look at the specific opportunities and constraints associated with those options. What are physical obstacles? For example, are there watercourses, rivers, roads, built-up areas, topography? So then we move on to outline design. At this point, we then get detailed surveys. So in the design, we must define the track gauge, the number of tracks, the horizontal and vertical alignment, the cant and cant deficiency, structure gauge, and track structure. So the coursework you're going to be doing this trimester is going to be based on basic mapping and producing outline designs for a new high-speed route. So when we move on to detailed design, we're going to start to use software to determine the earthworks in relation to vertical and horizontal alignment. We're going to calculate areas of cut and fill. We'll try and balance this to save on earthworks costs. We might have done some specific geotechnical investigation, which allows us to understand the properties of the soil, and that might have implications on the design. And then we're also going to start to look at supplementary features such as signalling, stations, etc. And we're going to have to produce specifications and contract documentation and issue these for tender. So once we mobilise a contractor, they're going to commence with the setting out of the rail alignment. And that's the job for the civil engineering surveyors with their theodolites, levels, total stations, robotic total stations, or even drones. Then we're going to clear the site, and typically construction will be undertaken simultaneously on different sections of the route. So there'll be a number of sections or work phases, if you like. The contractor's going to have to ballast and lay track. They're going to have to tie in with an existing route. And then eventually everything has to be tested and commissioned. And once all this has taken place to a satisfactory standard, then we're going to open the line for passenger or freight service. So in order to understand what we're going to design, we need to know what the scheme looks like, where it's located. This drawing of a Spanish railway just shows at a very high level the new routes, some of the new stations, key infrastructure, and also how the railway will align with the existing infrastructure. So as we progress with our design, we'll have to look at horizontal and vertical alignments, and we'll have to produce longitudinal sections through the railway. We'll have to pay particular attention to gradients and also the radius of the curves, and that depends on the line speed of the track. So let's start off with looking at the physics of railway curves. So let's start off by looking at Isaac Newton's three laws. Law 1. Unless acted on by an external force of some kind, an object will remain at rest or uniform motion in a straight line. Law 2. the acceleration of a body is directly proportional to, and in the same direction as, the net force acting on the body, and inversely proportional to its mass, F equals ma. The third law is when one body exerts a force on a second body, the second body simultaneously exerts a reaction equal in magnitude and opposite in direction to that of the first body. So speed is a scalar measurement. It has magnitude but no direction, whereas velocity is a vector measurement. It has magnitude and direction. Acceleration is also a vector measurement. It also has magnitude and direction. For a train moving around a curve, its speed is constant and it will have acceleration towards the centre of the circle. So based on Newton's second law, force equals mass times acceleration, the radial or centripetal force is the mass times the acceleration, which is the force that results in the acceleration towards the centre of the circle. So if we look at the centrifugal force now, we consider Newton's third law. So when a body exerts a force on a second body, the second body simultaneously exerts a reaction equal in magnitude and opposite in direction to that of the first body. So the reaction or centrifugal force is equal and opposite to the centripetal force, which means that the track feels as if it's being pushed outwards by the wheels. The centrifugal force acts horizontally at the centre of gravity of the vehicle. So a centrifugal force applied means that passengers on the train feel discomfort. As the speed increases, this force increases, and at higher speeds it may start to become intolerable for the passengers. It also increases the risk of derailment. Methods of reducing the effect of this force is through the application of Cant. Passenger comfort is important. Catering on trains is also important. It's not a new concept to have restaurant cars on trains, but here you can see a modern day version where Starbucks have installed one of their own cafes in a double-decker train. So let's now have a look at the application of Cant. The term cant is the vertical difference in height of the two rails of track, measured at the centre lines of the heads of the rails. So we're now going to look at the application of cant. So we're going to consider a train travelling along a straight track with no cant at a constant speed. Since the weight of the vehicle is acting vertically downwards through the longitudinal axis of the track, the weight is evenly divided between the wheels. So we're going to have the following symbols: M, mass, the vehicle mass, kilograms; G, gravity; Q, the wheel weight; E, subscript A, the applied cant; and S, the distance between the centres of the wheel, the rail contact patches. So if the vehicle is just standing on a piece of track that's horizontal with no cant, if you like, the wheel weight will just be the mass times gravity divided by 2, because there's two wheels, one on each side. So what we've done now is introduce cant. So the weight of any object on the vehicle floor will resolve into two components. The relationship between the two components can be expressed by the triangle ABC. So the triangle ABC is such that AC represents the mass times gravity, AB represents T subscript M, which is the force in the plane of the rails, and BC represents P subscript M, the force perpendicular to the plane of the rails. ABC is geometrically similar to triangle IOF. So for triangle IOF, IO represents S, the distance between the centres, OF represents the applied cant, and IF represents the square root of the distance between the centres squared minus the cant squared. Because these triangles are similar, we can then show the relationship between the variables. So therefore the force in the plane of the rails is T subscript M, and the force perpendicular to the plane of the rails is P subscript M. So now we'll look at the subject of equilibrium cant. So if we're on a curved track, we know the centrifugal force is equal to the mass times the velocity squared divided by the radius of the curve. If the force is applied to an object within the vehicle on a curve with no cant, the force will act horizontally on the object. If the force is large enough to overcome the friction between the object and whatever the object's sitting on, the object will move outwards. If the object is a passenger, he or she will feel discomfort. So if the track on a curve is canted inwards, the centrifugal force can be resolved into two components. Triangle AJK is similar to triangle IOF, so the force on the plane of the floor is T subscript C. The force perpendicular to the plane of the floor is PC, where PC equals the mass times the velocity squared over the radius times the cant squared divided by the distance between the centres of the wheel. So we've got all four forces acting through the object at point A. P subscript M and P subscript C are in the same direction and combine to form the weight on the vehicle floor. T subscript M and T subscript C are in the opposite directions. So the net force on the plane of the floor is T. And since the cant is small compared to S, the middle term tends to unity. So we can calculate T. So we now know the net force on the plane of the floor, T. But if V squared over R equals gravity times the cant divided by the distance between the centres, then the net force would be zero, i.e. our cup of coffee is going to stay on the table. So for the net force on the floor, T to equal zero, the component V squared over R must equal gravity times the cant divided by the distance between the wheels, and by transposition we can get what's known as the equilibrium cant. So consider this as a cant that ensures that your coffee sits on the table. So equilibrium cant is the cant at a particular speed at which the vehicle will have a net zero resultant force parallel to the running plane of the rails. So we've shown the equation for equilibrium cant, but there are terms in this equation which are effectively constant, i.e. the standard gauge and the value of gravity. So we can rewrite this equation as 0.1532 multiplied by the velocity squared divided by the radius. So in practical terms, it's also a little bit inconvenient to express cant in meters and speed in meters per second. So if the speed is in kilometers per hour and the equilibrium cant is in millimeters, then for standard gauge we can use the term shown. So now we'll look at what we mean by the term Cant deficiency. So equilibrium cant can only exist at one speed for any combination of cant and radius. But different trains travel at different speeds, for example a passenger service or a freight train. If the speed is higher or lower than the equilibrium speed, a deficiency or excess of cant will exist. So we can rearrange the equation for the net force, T, as shown. So the net transverse force is proportional to the difference between the equilibrium cant and the actual cant, and this difference is known as Cant deficiency. If the difference between EQ and EA is represented as D, then T equals the mass times gravity times D divided by the space between the rails. For comfort and safety, we place limits on D. Excess cant can also result in severe rail wear. So cant deficiency is the permissible shortfall in cant. The maximum permissible speed on a given track is governed by the value of applied cant plus the maximum permissible shortfall. So the calculations so far have been based on an object on the vehicle floor, or a table. If we now take the vehicle as a whole, the forces will act about the centre of gravity with a height h above the rail. We're now concerned mainly with the risk of overturning of the vehicle, and in particular, what cant deficiency that will occur. So through a similar mathematical proof, we can find the term for D naught, which is called the overturning cant deficiency. So now we'll have a look at what happens when things go wrong with cant. So one of the most severe mainline curves in Britain is in Morpeth in Northumberland. It's a 340 metre radius. The track turns through 98 degrees. The immediate approaches are straight lines with 125 miles per hour speed limits. The curve has a speed restriction of 50 miles per hour, I think, and has seen serious derailments in 1877, 1969, 1984, and most recently in 1994. So in 1984, the southbound sleeper service from Aberdeen to London was derailed at the same location. There were no fatalities, but 29 passengers and 6 train crew were injured. 2 houses narrowly escaped being demolished by the derailed carriages. The train was estimated to have been travelling between 85 and 90 miles per hour. The train involved was led by a Class 47 locomotive. The driver involved in this accident, Mr. Allen, was prosecuted for being under the influence of alcohol, but acquitted after what was described by the Expert Witness Institute as an ambush defence. Mr. Allen had consumed alcohol both before and after booking on duty, but the defence countered that he had suffered from bronchitis and had in the past experienced severe coughing fits that had caused him to fall unconscious. So now you've got an understanding of the physics and the calculations that take place in the railways to ensure passenger comfort and make sure your coffee stays safely on the table. So now we're going to have a look at the selection of a horizontal alignment. So ideally railways should follow a straight route, but this isn't always possible. What gets in the way is topography, geography, geotechnical and land ownership issues. Therefore, a railway comprises of straight lines, circular curves and transition curves. So there are a number of different types of curves. First of all, they can either be left-handed or right-handed. We can have simple curves, which are 2 straight sections are joined by a circular curve of constant radius, or a transitioned simple curve. Transition curves are added to one or both ends of the circular curve. A compound curve, 2 straights are joined by circular curves at different radii but with the same hand of curvature. Or reverse curves, where 2 or more curves of differing hand follow one another without intervening straight track. So let's have a look at curves in Cant. So we know the practical equilibrium cant, and on a given radius, the equilibrium cant is proportional to the vehicle's speed. So if speed on a curve is constant and consistent, then a theoretical equilibrium cant is possible. In general, speeds being consistent is only on a closed system, i.e. a single mode railways such as metros or dedicated high-speed lines. The majority of railways are mixed mode, and so will feature a variety of different traffic travelling at different speeds. So if we use the maximum speed of a passenger train to calculate cant, passenger comfort will be ensured. The forces Tm, Tc will be balanced. However, for a freight train travelling at a lower speed, Tm will be much greater than Tc, and this means that a substantially larger force may be exerted on the lower rail, which could damage it. And trains can sometimes even get stuck on curves. Conversely, if we use the maximum speed of the freight train, passenger comfort will be compromised. So for the passenger train travelling at high speed, Tc will be much greater than Tm, and as a consequence, there'll be wear on the outer rail of the curve, and passengers may also lose their cups of coffee. So therefore, we need a compromise between both situations. The compromise needed is a Cant value which is tolerable to passengers, but also produces only moderate track stress. So if E subscript A denotes the applied Cant, with a Vmin and a Vmax, denoting the speeds of the lower and higher speed traffic, then the applied Cant must be greater than EQ Vmin, but less than EQ Vmax. So the applied Cant is the actual value of the Cant that's applied to a curve. In most cases, it will not be the same as the equilibrium Cant. So Cant deficiency is the difference between the equilibrium Cant for the maximum permissible speed and the applied Cant. So Cant excess is the difference between the applied Cant and the equilibrium Cant for the lower speed traffic. So if we let D denote Cant deficiency, for the maximum permissible speed, the deficiency equals the equilibrium Cant minus the applied Cant. So we know the practical equilibrium Cant equation, so we can now drop in EQ is the applied Cant plus the Cant deficiency. So for comfort and safety, we place limits on the applied Cant and the Cant deficiency, and by implication, the speed. So if we define Emax as the maximum amount of Cant that can be applied at a given location, then the maximum potential speed is given by the equation shown, Vmax. So when designing a new alignment, the designer must take into account the type, speed and variety of trains that will use the line. And you can see a tabular example below. Here you can see an extract from the Network Rail Design Handbook. You can see the normal design values of Cant and different parameters or constraints, and the maximum or minimum design values. You can see extension of that table looking at plane line, adjustment switches, through route of S and C, and turnout route of S and C. Here you can see values of Cant, Cant deficiency and Cant excess for different traffic classes and different maximum speeds. Often a percentage is quoted for the proportion of Cant deficiency, and this is known as the ED ratio, and it's expressed simply as shown below. There are various tools and equipment you can use for measuring Cant, and this is a track gauge tool, which can also measure Cant. Network Rail now use a Network Rail measurement train to measure Cant across the network. I'll put up a YouTube video on the virtual learning environment that will show you the details of how they do this. So let's now look at what we mean by transition curves. If track on a curve is canted and the adjoining straight track is level, the introduction of Cant would result in a sudden movement. So there's a need to introduce a Cant gradient. And for optimum comfort, Cant should be introduced gradually, and this is done using what's called a transition curve. There are two types of transition curves. Commonly used in the UK is the clothoid spiral, but common elsewhere is the cubic parabola. So for passenger comfort, the rate of gain or loss of Cant under Cant deficiency needs to be restricted. So we can calculate the time required for a train to traverse a transition curve. So now to calculate the change in time, and the rate of change of Cant or Cant deficiency is obtained by dividing the change in Cant or Cant deficiency by the change in time. The length of a transition curve is taken as the greater of these two values. A virtual transition is sometimes used in place of a real transition. No real transition is installed. Instead, the radius changes instantaneously at a point. The length B can be considered a transition. B is taken as 12.2 metres based on the shortest wheelbase of British coaches. Cant is to be gained over this length. So let's now consider clearances. So end throw is when a vehicle is on a curved track and its corners overhang the rail to the outside curve by an increased amount to which they overhang when on a straight track, and this increase is known as the end throw. So centre throw is when a vehicle is on a curved track to the inside of a curve, the middle of the vehicle has an increased overhang, and this is known as the centre throw. Both the end and centre throw must be included together with the effect of Cant in calculations for clearances. So we can calculate the maximum centre throw in millimetres and the maximum end throw as shown. So I've seen a couple of really interesting examples of precision clearances. Let's have a look at two of them.
Here it comes. Here it comes. Này hút xong rồi đây ha.ให้มะเขือขยับก่อนดิไปเลยมันถึงจะออก Yeah, I think Thai people would be great tailgaters.
And then finally, a new high-speed line in China. I did ask myself, I wonder what was built first. So now we're going to look at the subject of buffer locking. So we've got issues with potential buffer locking on reverse curves. And when coupled vehicles pass from one curve to another with little or no straight track between the curves. And this results in relative lateral movements between the contiguous buffers. Taking oscillation, track and vehicle tolerances into account, there is a possibility of the buffers locking, and this may cause a vehicle derailment. So we need to check the relative lateral movement between the buffers, and this should typically not exceed 300 millimeters. And here you can see the calculations of how we take into account the radius of the curves, the straight length, the length of the vehicle over the buffer heads, and the distance between the bogie centres to calculate the relative lateral movement of the buffers. So now we're going to have a look at vertical alignment design. So the general objective is to follow the ground profile wherever possible. That's not always feasible, particularly in challenging topography. Longitudinal gradients of railways are much lower than those of highways. Gradients tend to depend on the power characteristics of the rolling stock used on the line. When it's not possible to follow the ground profile, a combination of earthworks, tunnels, bridges and viaducts will be required. All such measures are expensive to construct and also to maintain. The railway, not following the ground profile, will also have a higher environmental impact. The solution is often a compromise between cost of construction and line speed or journey time. The steepest line in the UK is the Lickey Incline near Birmingham. It has a 2.65% gradient over 3.2 kilometres. And this image shows a high-speed line in Germany, where you can see the horizontal and the vertical curves just at the end of the line. Here's a picture of the Guangzhou high-speed line. Note that the bridges and tunnels comprise 83% of the 857 kilometre length. Here's an example of a spiralling section of track in Myanmar. You also see some impressive spirals in Switzerland too. So in terms of vertical alignment, typical gradients for mixed traffic up to 200 km per hour will be between about 1.2 and 1.5%. For high-speed passenger-only traffic, this could be up to 3.5% or 4%. Compared to a typical motorway gradient in the UK, which will be about 3%, and standard roads a maximum of 6%. Beyond 4%, adhesion becomes very problematic, and rack railways are usually considered instead. In case you were wondering what a rack railway is, here's an example of one in Austria. So for vertical curves in the UK, there's a maximum permissible gradient change. This is shown as 0.2% or 2 millimeters per meter for speeds up to 125 miles per hour, and 0.1% or 1 millimeter per meter for speeds over 125. So we have two gradients, I1 and I2, intersecting at point K. A curve will be required if this change in gradient is greater than 0.25%. So then we'll have to calculate the radius, the vertical radius, R subscript V. For high-speed tracks, i.e. velocity greater than 200 km per hour, the vertical curve radius, R subscript V, is given by the equation shown below, where A subscript V is the vertical acceleration with a recommended limit value of 0.22 meters per second squared. So we can calculate the tangent of the arc, and then we can work out the ordinates of the vertical transition arc. So some other things to consider. No change of gradient should normally be made where horizontal transition curves exist. Vertical curves should terminate at least 5 to 10 meters from switches and crossings. Vertical curves should be avoided on steel bridges without ballast. So now I'm going to introduce you to some of the basic concepts of tunnelling and look at some railway tunnels in particular. So early tunnels were often dug by pick, shovel and blasting using explosives. A very labour-intensive process, which was extremely dangerous as well. In London they used what's called cut and cover techniques, where they excavated the ground in the street, constructed the railway tunnel, and then buried it, and then reinstated the street on the surface. Here we can see a modern cut and cover technique being adopted in Delhi, in India. So cut and cover tunnelling techniques are only suitable for close to surface lines. They're a relatively cheap and safe method of construction. It causes major disruption to the streets during the process. Buried services can be a major obstacle, and care needs to be taken with the settlement of nearby buildings, and this was quite a significant problem in Amsterdam with the North-South Metro line. Very early on, it was recognised that automation and mechanisation would help the process of tunnelling, and here we can see an artist's impression of a tunnelling shield being used to construct a masonry tunnel. The tunnel shield as we know it was developed by Mark Brunel. It was developed to tunnel through waterlogged ground, and it consisted of 36 closed cells on a cast iron frame. Jack boards opened one at a time and were then excavated. So the idea was refined by James Greathead in 1869. The Greathead shield principle is still used in soft tunnel excavation. The manpower was replaced with hydraulic jacking, and this then followed with the tunnel lining. And here you can see a tunnel lining constructed from steel rings which are bolted together. Another technique is to use precast concrete rings, and here you can see the sections stacked up ready to be taken underground. Another technique is to spray concrete. Here you can see the reinforcement, followed by the sprayed shotcrete lining. So in Crossrail they used what was called a tunnel boring machine. Clearly you need a rather large project or large tunnel to justify such an expenditure on a complex piece of equipment.
Construction of Crossrail began in 2009 in Canary Wharf, and since then we've seen a huge amount of progress, with our construction programme running at peak between now and 2015.
While last year the Olympics were happening and the world's largest sporting party going on, we've been building Europe's largest construction project underneath all the partygoers, and really without anybody noticing what we were doing.
We're building new stations throughout London, but in order to deliver that new railway, our tunnelling machines are hard at work right now, driving the new tunnels.
For us, it's our underground marathon. It's our 26 miles of tunnel that we're working our way through. And of course, here at Farringdon, is the finish line of our marathon, where 4 of our 8 machines will finish. There's an extraordinary amount of work going on, 8,000 people across 40 sites. And above us we have London, one of the world's busiest cities, going about its daily business.
These machines are 7 metre diameter. Each one of them costs around £10 million, 1,000 tonnes in weight. They're 150 metres long, so these are big underground factories.
We're in the westbound machine at Victoria. We're about 1,000 metres in from our launch. We're at the business end of the machine. It's here that we excavate and we build the rings. It's a sometimes frantic but always controlled pace in which they work. So communication, understanding of what their colleagues are doing is the most important thing.
Tunneling on Crossrail is more than the 8 tunnel boring machines and 10 drives that they'll do. Across the whole of London, we're creating these caverns using sprayed concrete lining, which allow us to create the platform tunnels for the stations, and those allow the TBMs to come through. These caverns are 17 meters wide by 15 meters high by 50 meters long, which makes them some of the largest structures that will be built with sprayed concrete lining in the world. We've got tunneling still to do this year and next year, which will allow the rail systems contractors to get in and put the railway through the tunnels for its opening in 2018.
All of these tunnels, all of these big holes in the ground are about creating a new railway for London. One that in 2018, overnight, will increase the capacity of rail in London by 10% in a single step, the biggest single step ever.
So now we're going to have a look at bridges. So brick or masonry stone arches form many of the early permanent railway bridges in the UK. The method was proven from earlier construction of roads and canals. The structures proved to be very strong, and even hundreds of years later they're still in service. Support and the foundations need to be robust. Water ingress is the main issue, so maintenance, i.e. careful attention to drainage and pointing. Generally they're not used for modern construction, but form a significant part of the railway maintenance work. Cladding in modern structures can give brick stone appearance if required for aesthetic purposes. Here's Brunel's Maidenhead Bridge and the Culloden Viaduct. Riveted wrought iron was used originally, followed by steel. Early metal structures followed an arch form. They mostly resulted in an iron being in compression, so they formed a sound structure. Early steel bridges were hot riveted, but laterly welded. Medium span steel bridges based around the large I-beam. Longer span bridges used box girder sections, and very large spans used lattice or truss designs. So now just show you a couple of images showing these different bridge types. And of course the iconic Forth Bridge. Concrete is generally good in compression. Reinforced concrete is fine for bridge piers, but due to the dynamic loading on large spans, reinforced concrete is not suitable for railway bridge decks. Pre-stressed concrete is a preferred material for bridge decks. It's usually delivered to site in sections and stressed on site for rapid installation. And typically there'll be an epoxy mortar or grout used between the sections. Here's a very early example of reinforced concrete construction in the Glenfinnan Viaduct in Scotland. And here we can see a concrete viaduct being constructed in Spain for a high-speed line. Another structure on the Spanish high-speed line, the AVE, this time in Malaga. So now let's have a look at the subject of level crossings. So there's approximately 6,000 level crossings in the UK. They're mostly private crossings or footpaths. There's about 1,400 level crossings that involve public roads, and level crossings are one of the largest safety risks on the railway. So these figures were taken from Network Rail's website. You can see that over the years there's been a number of issues associated with collisions with road vehicles, trains striking pedestrians, near misses with road vehicles, and so on. So I'm now going to show you some images from the level crossing incident in Dusseldorf in Germany on the 20th of December 2012. And from these images you'll get an appreciation of the scale of the damage that this can cause, not only to the road vehicle that's struck, but the locomotive, the train, the track infrastructure, and in some cases the surrounding buildings. So now I'm going to have a look at some of the different types of level crossing. So you can see an open level crossing. These can either be controlled locally or monitored remotely, but you'll see that there's no barriers, there's no physical barrier that comes down that stops the cars from driving across the track. Here's an example of an open level crossing up near Fort William. So you can see a manually controlled barrier with gates. And here's an example. Here we can see the gates being closed. Here's a full barrier level crossing, where we can see the barriers come down across both lanes of the road. So this is a half barrier level crossing. And here's a real life example of a half barrier level crossing system. So you can see that with the half barriers, if somebody was foolish enough to want to cross the lines when the signals were at red, then they could drive round the barriers. So I'm going to give a separate lecture on the subject of level crossings because it's quite complex. In particular, the various systems that are used to identify vehicles on the track when the barriers are closed, and also identify potentially people or objects on the track. So what can go wrong at level crossings? I'm just going to show you a short video where we can see some of the human behaviour that we have to deal with as railway engineers when we're dealing with designing or controlling level crossings. So how do we prevent accidents at level crossings? In some cases we put cameras in vans near level crossings to observe behaviour. Or we can install static cameras that we see at red lights in the cities. We can also consider automatic image detection. Here you can see a camera identifying the car and the pedestrians walking across the track. The safest thing to do with a level crossing is to remove it completely, and here we can see one being removed and replaced with an underpass, but as you can gather from these photographs, that's quite a serious undertaking and would cost a substantial amount of money. Here you can see the Russian solution to stopping people travelling across a level crossing when the barriers are down. Quite an interesting innovation. So if you become a railway engineer, it's inevitable you'll have to get to grips with some design software. So new railways can generate multiple alignment possibilities. Due to the size and scale of a railway, this can lead to a substantial amount of calculations being required. So to help with that, you can use packages such as Bentley Rail or Autodesk Civil 3D, which expedite the process. A technical explanation of these softwares and how we use them is complex and way beyond the scope of this lecture. So I would suggest you spend some time looking at the Bentley or Autodesk website and find out more information on your own about the design software that's used. So that's the end of Unit 5. In the next session we're going to look at switches and crossings, in particular geometric design, speeds and clearances associated with them. So thanks for listening and bye for now.